Hi everybody, so in this video we go through the computation of the Lagrangian average vorticity deviation, also abbreviated as LAVD, on a two-dimensional velocity dataset. So in the previous videos we covered the FTLE and the PRA computation. Both of these methods relied on the previous computation of the gradient of the flow map. Now the LAVD tries to reveal, or actually reveals, elliptic flow structures starting from the vorticity along a trajectory. So the philosophy behind, so if I were to compare the LAVD to the PRA, I would say that the philosophy behind these two methods is quite different, because the PRA relies on the computation of the gradient of the flow map, whereas the LAVD is, let's say, a more physically related quantity, because it just involves the computation of the vorticity averaged along a trajectory, simply speaking. So let's see how we do this computation of the LAVD. So the LAVD folder contains, again, the main folder where the main notebooks are contained, and then two other notebooks. One notebook is called find outermost contour, and we will see later what this does. And the other notebook simply takes care of the LAVD computation. So the LAVD is fairly simple to calculate. So the general philosophy is that you have a trajectory over some finite time interval. And together with this trajectory, you also have the vorticity along this trajectory. Now, how the LAVD is defined is you simply take this vorticity and subtract the spatial average of the vorticity at a specific time. So what you basically do is you compute the vorticity for a set of trajectories, and then also you compute the spatial average of the vorticity at each point in time. Now, of course, when you compute the spatial average, you need to define a spatial domain. So the spatial average is always with respect to a spatial domain. And then you basically take this quantity, so you take the vorticity, subtract the spatial average, and integrate the absolute value of it along a trajectory. With that, you then can associate to each trajectory or to each initial condition the corresponding LAVD. Now, of course, sorry about that. Of course, so this involves an integration, and we numerically approximate this integration with this formula here. What this LAVD function takes as input is it takes as input the vorticity along a trajectory. So basically, you first compute the vorticity along a trajectory. This omega, which I called, is simply an array which has the vorticity computed along trajectories launched from an initial grid. And ny and nx simply specify the y and x components of the grid, and nt is simply the time. And then, of course, you also need to pass as input times, so the time array. We assume that the spacing of this time array is uniform. As an output, you then simply get the LAVD. So before you actually compute the LAVD, you need to first compute the spatial average of the vorticity. And then you use the spatial average and integrate the vorticity along the trajectory, but you need to subtract the spatial average at each point in time. So it's actually fairly simple to compute. Now, let's go back. Before we take a look at this find outermost contour, we actually go back to the main scripts. Now, in this main script, actually, so of course, the import statements are always the same. Here, we need to input the LAVD folder additionally. And the procedure is, again, the same as in the FTLE and the PRA. So the first 4 steps are exactly the same. Import data, define parameters, define spatial temporal domain, and interpolate the velocity. And then the 5th component is computation of the LAVD. So we proceed by first computing trajectories launched from a regular grid. Then we compute the vorticity along these trajectories. The vorticity is simply the curl of the velocity field. And once we have computed the vorticity along all the trajectories, we then pass basically this array into the LAVD function, which I've shown previously. And what the LAVD function does, it simply computes the LAVD associated to an initial condition. Then once we have computed this LAVD fields, which you can then again think of as a scalar diagnostic quantity, where you basically plot the LAVD over the set of initial conditions, you then would like to have a method which extracts closed curves related to vertical flow structures. So when we basically then need to extract vortex boundaries from the LAVD using the algorithm proposed in the reference one. With the reference one, you can look it up then in references. It's basically a paper by Professor George Haller from 2016, I think. So the first 4 steps, import data, define parameters, are the same. We focus on the step where we compute the LAVD. Of course, again, when we compute the trajectories, we parallelize the procedure. So basically, we split all these trajectories into several batches and then compute these trajectories in a parallel fashion. That's why I have this parallel omega function. So what this function does is it defines an omega array. This omega array has, of course, the size of the mesh grid first. So the mesh grid over which you launch initial conditions, and then, of course, the size of the time. So the last dimension is over the time. You define the initial conditions. You then compute the trajectories simply using the integration function. So that's something we've already covered in one of our introduction tutorials. Then, of course, here you need to make sure that when you compute the trajectory, actually the trajectory is not landing outside the domain of the boundary. So this is simply just like a check where when you compute the trajectory, you actually want the trajectory, of course, to be inside the data domain. If it's outside the data domain, you need to discard this trajectory. This is just like a safety procedure. And then finally, you compute the vorticity along trajectories by first computing the gradient of the flow map. Sorry, not the gradient, the gradient of the velocity, then the spin tensor, and then from the spin tensor, you compute the vorticity. This is one way you can compute the vorticity along trajectory. Simply by first computing the gradient of the velocity field, then you take the antisymmetric part of this gradient of the velocity field, you compute the spin tensor, and then from the spin tensor, you can then extract the vorticity, of course. Once we've done that, so once we've computed the vorticity along the trajectory, so once we've computed this omega along the trajectories, we can then pass this omega, which is now an array, right? So it's an array of dimension ny, nx, and nt. And you simply pass this omega, so basically the vorticity along all trajectories, into the LAVD function. So this function then computes the LAVD. What the LAVD then simply is, so the shape of the LAVD is then simply the shape of the mesh grid, right? So it's simply ny. So the first dimension simply corresponds to ny, and the second dimension simply corresponds to nx. So you can see LAVD shape is 161.91, where ny is 161 and nx is 99. So that's simply the spatial temporal domain which you've defined with the corresponding resolution. So this is simply a scalar diagnostic. You can then plot the scalar diagnostic over the spatial domain, and what you get is such a field, where of course you view vortices as regions with high LAVD values. So all these regions are candidates for vortices. Now, what you want to have actually is you want to have a precise criterion from these scalar diagnostics. You eventually want to have want to extract the outermost vortex boundary. The way you do this is through this find outermost contour function. So what this find outermost contour function does, and I've defined it actually I've also defined it here in the LAVD folder. So we can now take a look at this find outermost contour function. What it does is it extracts the outermost vortex boundary from the LAVD field, where we define. So how do we proceed here? We proceed by first, we first look for the vortex centers, and these vortex centers, they are defined as local maxima of the LAVD. So basically, we take a look at this field here and identify all these local maxima. For example, free dominant or free clear local maxima are this one here, right? And then we focus on this local maxima, and we seek initial vortex boundaries, which we now call B, as the outermost closed contours of the LAVD field, satisfying all of the following conditions. So of course, these vortex boundaries, they need to encircle a vortex center. Then these vortex boundaries need also to have an arc length, which is above a certain threshold, L min. So this is something which you need to specify. It's basically the expectation that you have about the perimeter of the vortex boundaries. So basically of the side of the vortex. And then the last condition is the convexity deficiency. So the convexity deficiency is simply a value which tells you how convex this vortex is. So of course, this convexity deficiency, so if this convexity deficiency is 0, it means that you have a perfectly convex structures. However, generally you want to be a bit more forgiving, and you might allow for some slightly non-convex structures, and that's why you have this convexity deficiency. These are all the parameters that you, so the parameters you need to specify is basically, of course, when you compute these vortex centers, you need to specify, so you look for local maxima, and you need to specify how, when you look for local maxima, you need to specify how far, for example, they are placed, right? So you need to specify the minimum distance between local maxima. Then you need to specify also the resolution of the contours. So this is just, of course, how fine you want to be when you compute these contours. The convexity deficiencies, we already had that, and the minimum eddy parameter, which is L min. Then you can also define a threshold on the local maxima. The number, of course, are just simply used for parallel computing. And the last one is simply a list which stores the vortex boundaries. So the parameters you need to specify is basically distance, the resolution of the contours, the convexity efficiency, the minimum eddy parameter, and if you want, also the local threshold on the local maxima. So the threshold on the local maxima of the LAVD. So these are all the parameters you need to basically pass to this function. And then this function simply outputs the vortex boundaries. So this vortex here is just like a list which contains all the vortices. So that's the function. And in the main script, we just simply need to call this function. So we need to specify all these parameters in the main script and just pass them to this function here. Of course, this function takes as input also the grid, so X domain, Y domain, and the LAVD field, of course. And then as an output, you get this vortex, and this vortex, as you can see, is simply a list. It's simply a list, and of course, the length of this list is the number of vortices you have detected in the data set. So here, the length of vortex is simply 3, so which means that the algorithm detected 3 vortices in the data set. And then you can plot these vortices superimposed on the LAVD, and you can see that you get these structures. Now, these structures are similar to what we were getting from the PRA computation. So I invite you to check out the PRA script we already had, and you can see that these structures match quite well. Now, something you could try is, of course, you can, for example, increase the convexity deficiency. So it originally was 10 to the minus 6, and I can increase now to 10 to the minus 3 and run this algorithm. And you can see if I increase the convexity efficiency, so if basically I allow the structures to be less convex, then the vortices I get will be bigger, right? Because I'm a bit more forgiving. Now, the same thing, I invite you to try out and change these parameters. So you're free to change these parameters and see how the structure changes. With that, I want to thank you for your attention, and I look forward to the next video.